Is this loud enough? Do I need to be louder?
Be a little louder.
Like this?
Yeah.
So like I'm talking to right over there.
Yeah.
Okay. All right. So you want me to start from the top?
Yeah.
Okay. So first we have the free body diagram, Newton's methods, stuff we did in Physics 1. So it's not that bad. Two examples here. You've got object in free fall with no air resistance. You have a spring on the surface here. So you're looking at a free body diagram. So here you've got gravity is pulling this down. There's no resistive forces, so you don't have to put anything up here. You know, velocity is going down, but that's not really playing too much right now. So gravity, well actually it is a little. So gravity, velocity, mass of the object. So the kinetic energy is, in the book we're using T, but when we took Physics 1 we were using K. Sometimes problems use U, sometimes they use V. So this is potential energy, this is kinetic energy. These are the specific forms for this specific problem, but they change depending on what problem you're talking about. So for this, kinetic energy is 1/2 times the mass times the velocity squared, and the potential energy is mass times acceleration times the distance that it's traveling, so gravity times height. Kinetic energy for here is 1/2 kx squared, or is that potential energy? Do you have that in your notes?
I'm checking right now. 1/2 kx squared.
Yeah, I know it's one of them. Don't remember which one.
Oh Lord, it's gonna take forever.
Damien, do you remember 1/2 kx squared? Is that potential or is that kinetic energy for a spring?
1/2 kx squared?
Yeah.
What is it for falling?
Well, so this is for a spring though.
But it's the same thing. It's just kx. You switch the v out for x.
So that should be kinetic energy, is what you're saying?
Yeah.
Okay.
The same thing as kinetic.
Okay. All right. But yeah, so basically you've got the free fall, you have projectile motion. So free fall, projectile motion, springs, pendulums. I think you can do it with circular motion, central forces as well. And that's the Newton's method. Energy method, for again all those same problems, you start with whatever your kinetic energy is, whatever your potential energy is, and then the total energy is your kinetic plus your potential. So that's pretty simple for those. Any questions on those parts before moving on? So then the other one that was covered a lot, even more than either of those, was the Lagrangian. And that's, so you find the Lagrangian by taking the kinetic minus the potential. So with this problem, that would be, may as well write it down. Is that big enough for the camera to pick it up?
Nope.
Right, like you wrote the E equations.
No, fine. That's
1/2 mv squared minus mgh.
All right, cool. So Lagrangian equals this. And then to be able to solve that, to find your equation of motion. And for equation of motion, that's just, so sum of your forces is equal to mass times acceleration. And you can find that through all three of these methods. So you start with this, and then this right here. So you take the derivative of this with respect to whatever components you're looking at. So this one, so first this whole thing, so this is d dt of dl dqk dot minus dl dqk, and that's so this is just generalized coordinates. So this works for Cartesian, spherical, cylindrical, polar. Just plug in for QK and Q dot K, whatever your
So
coordinate
it's
is.
DL over DQK. It can work for all the equations?
Yeah, so this part here, so like if this was Cartesian, this would be dx dot or dy dot, for example.
Over DQ dot?
So like if I was to write the whole thing for the x component in Cartesian, that would be ddt dl
Or DX?
dx dot
Oh, okay.
minus dl dx equals 0.
Okay.
Um,
And then for the other one, it'd just be D over DT, DL over DY.
right, yeah.
Okay.
So yeah, so then you just plug in for here, that's whatever components you need.
Okay.
So with this one, you're taking the respect of your Lagrangian with respect to, in this case, this would be with respect to x, which there's no x component, so that would be 0. And then the derivative with respect to time, derivative of that, so forth. Do I need to work through one to give an example?
If you could, if
Okay.
you know it, work through one spring and one pendulum,
Mm.
if you can.
For working through those problems, or just like working through to show how the Lagrangian works?
Working through show how Lagrangian works.
Yeah.
Okay, I'll just go with this then since it's already up here.
Yeah.
So there's only one component that we really care about with this problem, and that's y. So this is, instead of v squared, I'm going to write v is equal to y dot for this problem. So instead I have to here, right?
Yeah.
Okay. So this is what we're looking at. So first, we're going to find this part with respect to y. That's going to equal, so this part is going to cancel out. That's all a constant for that. So this is going to be minus mg. And then with respect to y dot, this part isn't going to be there, but this one is. The derivative of y dot squared is going to be 2y dot, and that's going to be times 1/2, so that's going to cancel, leaving you with y dot.
Y. But wouldn't it be M2Y?
So this, so you'd be looking at 2 times 1/2 m y dot when you take the derivative. Those cancel.
Okay.
And then the derivative with respect to time of this, is going to equal m y double dots. So then if you plug that all back into here, you have this part, so this is m y double dot minus, this one is mg, so this is a minus, and this is a minus, so this will be a plus. Yep. Plus mg equals 0. So your equation of motion is going to be my double dot equals minus mg.
Okay.
So does that make sense?
Mm-hmm.
And is that large enough for it to see?
It should be when they're full screen on YouTube. It should be.
Cool. All right, so you've got Lagrangian, Newton's method, energy method,
Coordinates.
right, coordinate systems. So, coordinate systems, we went over Cartesian. polar.
Keep your voices down, cause we hear everything.
Hmm?
No, you good, cause we hear everything that you're saying.
Cylindrical.
We hear everything that you're saying.
If I'm talking at the board, is the sound reflecting enough for it to catch? Okay, so Cartesian, polar, cylindrical, and spherical.
Oh, it's still recording. You
Okay.
go ahead.
Yeah, so Cartesian, polar, cylindrical, spherical, those were the 4 systems that we went over in class. Just shift that over. Alright, we've got X, Y, Z components, R, theta,
Anybody got any?
R, theta, and Z, R, is it theta and phi? Is that what we're doing for spherical? Or are we using something else inside of theta? I think it's
Theta, phi, and Z. Okay, R, this symbol. Phi and Z. You got.
so we were using phi instead of theta for cylindrical.
Yeah, that's what we do in Bill's class. To at least keep you separated, to keep you different.
It can be theta, it can be phi, whatever you want to call it.
Yeah, it doesn't matter. That's why I didn't understand why he wanted us to derive cylinder coordinates. I can call these values anything. I'm just saying.
So I'm going to say theta and phi for spherical here too. So Cartesian, as an example here, you can say this is X, Y, Z. Polar, as you see, there are only 2 components, so you have to ignore the Z component. Polar, you've got your R, which is whatever the radius is out to your circle, and then your theta is whatever the angle is from your center line. Cylindrical, basically you're thinking this, but then you're also going to extend that out into the Z direction. So it's 3-dimensional. And spherical, can't really draw that well. But R is the same thing, it's whatever the radius is out from the center to your edge of your sphere. Then you have a component from your, so if you're going to look at it, you have Cartesian here, here, and here. This one is going to be one of these, and this one is going to be the other one.
I'm sorry, my pencil broke.
Go.
Which one you said was coming out from the Cartesian? I know you said it's Y, X, and then you got the Z, but
So for what these relate to,
yeah.
I'd have to look it up again. I keep confusing them for theta and phi, which one is supposed to be which one. But one of those, if you're going to think of it in this way, one of them is this angle here, and one of them is this angle here.
Periodically check
Okay.
to make sure that
And you got
you're
one coming out, right?
Yeah, and so the one coming straight out to the edge of your sphere, that's R.
periodically
Okay.
check to make sure.
Okay, that makes sense.
So that one stays the same throughout polar, cylindrical, and spherical.
I broke my pencil. I'm not gonna fail. I just broke my pencil.
You gonna film? You can't write that down in the exam.
No, I got another pencil. This is my favorite pencil.
Alright, let's see. Coordinate systems, Lagrangian, energy method, Newton's method, orbital equation. Bruce, was there anything else with that you wanted me to?
I just need you to go over whatever was the basics.
So basics, is there anything basics with coordinate systems further that you need?